Right, welcome back Year 13s. Since you've been gone, we've found out how to make videos and things. So the Year 13 projectile work. It's two-dimensional motion under the effect of only gravity. Follows on directly from the Year 12 work we did with the SUVAT and the one-dimensional projectile work. Things just going up and then down again, up, then down again. The principles are straightforward. The questions can be more complicated, but that's A-level. So the principles are we work with horizontal motion and the vertical motion separately. Keep them separate. So it's like a lot of the two-dimensional component work. Now, how do we do that? How do we start with a speed at a given angle when something is launched? Well, we have done this before. We've used the same principle when you looked at components of forces. When you said that that component was F cos theta, and when you said that this component was F sine theta, in the last bit of work we did exactly the same thing. So if we take a speed at a given angle in exactly the same way as with the forces, we have a horizontal component and we have a vertical component. The only thing I'm going to correct from what I found on the internet is typically we're not going to use V at this point. We're going to be using U for the initial speed. Then we work completely separately. We keep the horizontal and the vertical motion separately. Horizontally, because there's no acceleration, S equals ut. Okay, everything changes but ux. The horizontal component of velocity stays the same. So the distance traveled is that multiplied by time. Vertically, because the acceleration is minus g, we're going to use SUVAT again, like we did in year 12, and those formulae are on the formula sheet. T will be the parameter that connects those two ideas in a question that involves simultaneous equations. And that is often what the best questions do in this case. So if you have a look at 17A, question 6 and question 9, I'll go through them. Now I've learned now that I don't actually have to stop speaking. You can pause the video while you read them. So in 17A, question 6, we've got a particle projected with a known speed and we know what the greatest height is. We don't know the angle is launched at. So what do we do? Well, this greatest height is one of the vertical ideas. It's one of the vertical quantities. So working vertically, list what we know, and we know u, which is the speed times sine theta. We know a is minus 9.8. At the greatest height, the vertical component of the speed will be 0. The vertical component of the velocity, sorry, will be 0. And we know that the greatest height is 8. So what are we trying to find? We're trying to find the theta. All of this information can be put into this SUVAT equation. Quote the equation for the mark, substitute the values in, and we get sine squared theta is 4/5, which will give us two answers, plus or minus 0.89, which would give us, within 360 degrees, it's going to give us 1, 2, 3, and a fourth answer. Of those four answers, only 63 degrees is valid. One of them is going to be obtuse and two of them are going to be reflex angles, which aren't valid in this case. Nice classic, working with the components and using the SUVAT work. Question 9 is a slightly more complicated one, but again a classic of its type. We're told the launch speed, we're told the angle it's launched at, then we're told that 6 meters away there is a wall 1.6 meters high. Does it clear the wall? Well, we know that at 6 meters there is this wall, so why don't we work out how high the ball is when it's traveled 6 meters horizontally? and then see if that's above or below the wall. So horizontally, everything changes but ux. Ux stays the same. So distance travelled is u times t. 6 is 12 cos 30 times t. Right, straight away we get an expression for the time taken. Well, if we know the time taken and we know the initial speed of a launch angle, then we can, working vertically, find how high it is at that time of root 3 upon 3. And then what we know the exam boards like is, so when x is 6 meters, the ball will be at 1.83 meters high. That's bigger than 1.6, the ball clears the wall. That should leave you in a position where you can do the other ones in 17a. Now, what I want to go on to this time, though, on this first video we're making, is my favourite bits of this. Okay, it's deriving greatest height and range equations, and also showing that the path of the projectile is a parabola. Some really nice algebra, a nice use of the work we did on the year 13 trig as well. So projectile motion, so deriving the expressions for greatest height and the range from and onto a horizontal surface, assuming there's no air resistance, and also assuming that g stays constant. So what do? Absolute way we do all the projectile questions, we work separately with horizontal and vertical. So horizontally, x is u cos theta times t. Vertically, we can use v equals u plus at. So what have we got there? So vertically, using v equals u plus at, at the greatest height, v is 0. So the time to the greatest height is u sine theta over g. The time in the air takes the same time to go up and down. That's a year 12 result, is twice that. Okay. Using v squared is u squared plus 2as. Also, that time in the air, we're going to use that over here. Now, separately, to look at the greatest height. If we use v squared is u squared plus 2as, at the greatest height v is 0. Vertically, we're going to use the vertical component. The acceleration is minus g. So we get this equation, which rearranges nicely to give us that. That always used to be a popular question, deriving that. Right, so that's the first one. That's the greatest height derived. Now, what about the range? If the time in the air is 2u sine theta g, and if the distance travelled is u cos theta times time, then that time can be substituted in here. And we get this for the range, 2u sine theta times u cos theta all over g. Okay, which is a good result in itself, but look at this bad boy. 2 sine theta cos theta sine 2 theta. So we've got two expressions there for the range. The range, how far it travels horizontally before it lands in the same place. Okay, now, some previously beautiful questions. Note that if you divide that by that, if you divide this by this, the u squareds cancel, one of the sine thetas cancels, g cancels, and you get this lovely result that the greatest height divided by the range is tan theta over 4. And that came up every so often, a question that gave you greatest height and range. Could you work out the angle and then onto the speed. And yes, you can by doing that. Right. So that previous result, if the range is this, which is this, then the thing about sine 2 theta is it's a trig function, isn't it? It's one of the periodic ones. It does that. It starts, and sine theta starts at 0, goes up to 1, comes back down to 0 again. So sine 2 theta has a minimum of 0, but it has a maximum of 1. So the range is maximized when sine 2 theta is maximized. That's when 2 theta is 90, which means theta is 45. Which hopefully is a result either you knew or thought should be true, that if you fire something off at an angle, it travels the furthest if it's launched at 45 degrees to the horizontal, if we ignore air resistance. Right, that also means that for any angle either side of 45, the particle's going to travel less far. So if we've got this trajectory for 45 degrees, which is the maximum, then for any other range which is less than the maximum, there will be two trajectories that get us to the same point. So there will be questions that say, what are the two possible angles to get a projectile to this point? And there might even be questions about why which angle might be the preferable one. Why might we want something to go up high and land in that spot and possibly not bounce very much further? Or why might we want something to land at a shallow angle and keep rolling? Right, it has always been, when we did EdXL for year upon year, deriving the greatest height and range equations has always been a popular question. And it's derived really nicely in the book as well. And every so often, using that was a lovely finish. Now, my next favorite question is a whole variety of families of questions, which is in section 2 of this chapter 17, trajectory of the projectile. Now, the trajectory of the projectile is a parabola if we assume that air resistance is 0, which if we're assuming it's a particle, we have assumed that. So remember the golden rules. Horizontally, x is u cos theta times t. Vertically, use suvat. Okay? If we say that the general point on the trajectory is xy, then x will be u cos theta times t, and y will be, well, instead of u, we're going to use u sine theta. Instead of a, we're going to use minus g. So we get this result. Y equals u sine theta t, take gt squared upon 2. Now, for those of you who are concentrating, we have x and y as a pair of parametric equations, which is a part of the pure work, isn't it? Remember, the pure is so that we can solve the mechanics and the stats problems. Now, if I want to combine a pair of parametric equations to get a single Cartesian equation, rearrange one of them to make the parameter the subject, substitute to eliminate, and then see what you've got. So, equation 1, t equals x over u cos theta. Sub into 2 and we get this, okay, which is that. So if we're assuming for a particular question that theta and u are constants, this is the equation of a parabola, isn't it? Because this is the equation of similar to ax take bx squared. So not only is it a parabola, but we know it's a parabola, and the pen's never as good, so I'm going to use the pen. It's a parabola that looks like that, isn't it? It's a parabola which is, like all parabola, symmetrical. And if I do that, from the previous work we've done, we can work out the greatest height, and we can work out the range. But and we like this finish, notice that little 1 over cos squared, which of course is sec squared, which of course is 1 plus tan squared. So they sometimes ask this as what we've got at the top. They sometimes ask you to derive that so they can test the year 13 trig, and they sometimes ask you to derive this so that we get not only a quadratic in x, but it's also a quadratic in tan theta. And I believe that a lot of the questions in 17b, well, first of all, worked example 17.7 is brilliant, and the questions in 17b are good, and there's mixed practice 17. I'm going to try and do some more videos of the topics we've got left for the mechanics are the moments. We might produce some video. If you like these, you can put a message on us so we can make some videos maybe for the forces in context. And if I give you, I might even give you the code to the year 12 mechanics site, and then you can look at the videos we're doing for the year 12 students. Okay, hope you're all keeping well. And I'll see you on the next video.